In this video, we're computing the integral of 1 over the quantity x squared plus 5 all squared. Now, this is actually a pretty difficult trig substitution integral, but it's actually one that pops out of partial fractions decomposition pretty frequently, so it's important to know how to do it. So what we're going for in our trig substitution is that we have a variable thing squared plus a constant. Well, if we could get a tangent squared plus 1 out of this, we'd be able to use the identity that tangent squared plus 1 is secant squared. So the way to get this done is that we're going to let x be square root 5 times tangent theta. Now when we square that, we get 5 tangent squared theta, and then we'll be able to factor the 5 out. Before we get into that, let's make sure to transform the differential. Dx is the square root of 5 secant squared theta d theta. And one more note up here before we actually transform the integral, we are going to have to change our final answer back in terms of x instead of theta. So it's nice to just go ahead and make a note of this right from the beginning, that if x is square root 5 tangent theta, then we find theta by dividing by root 5 and inverting the tangent function. So that's the inverse tangent of x over root 5. And we'll have to use that once we find our final answer in terms of theta. So getting into all these substitutions, this denominator becomes 5 tangent squared theta. Again, when we square the square root 5 tangent theta, we end up with 5 tangent squared plus 5, and that's all squared. And then in the numerator, we have square root 5 secant squared theta d theta. So in the denominator, if we factor the 5 out of that, well, that whole thing is still squared. So it produces a factor of 25, and we can move the factor of root 5 over 25 out in front of the whole integral. And we'll leave the numerator alone. In this step, we have a secant squared theta d theta. In the denominator, we have tangent squared theta plus 1 all squared. And tangent squared theta plus 1 is secant squared theta. And when I square that, I get secant to the 4th theta. Now, 2 factors of secant are going to cancel, and I have 1 over secant squared. But 1 over the secant function is the cosine function. So now I have root 5 over 25, integral of cosine squared theta d theta. Now this is a classic trigonometric integral. To integrate the cosine squared, we need to use the identity that cosine squared is 1/2 times the quantity 1 plus cosine 2 theta. So we're going to pull the 1/2 out while we work, and this gives us root 5 over 50. And then I have the integral of 1 plus cosine 2 theta d theta. Now each of these pieces is quick to integrate. The integral of 1 is just theta, and the integral of cosine 2 theta, I'd prefer not to use an explicit u substitution on that. It's really distracting inside a larger problem like this. So the antiderivative of this is essentially sine 2 theta, but we notice the chain rule would produce a factor of 2 if we wrote that down as the antiderivative. So we just cancel that out with a 1/2 in front, and there's the antiderivative of cosine 2 theta. Now at this point, we're going to put in an arbitrary constant c. And now it would be nice if we were done, but we have to express the final answer in terms of x. So that requires replacing theta with the inverse tangent of x over root 5. That's the angle whose tangent is x over root 5. And there's no problem making that substitution for theta in this first term. That's just going to be inverse tangent x over root 5. But there is a tricky issue in this second term. If I take the sine of twice the angle whose tangent is x over root 5, we're kind of stuck at that point. Now I can find the sine of the inverse tangent or the cosine of the inverse tangent, just not the sine of twice the inverse tangent. So what we're going to do is apply the trig identity that sine 2 theta is 2 times sine times cosine. And that 2 produced by the identity cancels the 1/2. And I end up with theta plus sine theta, cosine theta plus c. And now I can go ahead and sub in theta because I know I can always compute a trig function of an inverse trig function algebraically. So there's the replacement on the first term, theta, and that piece is done. And then I have the sine of the inverse tangent of x over root 5 times the cosine of the inverse tangent of x over root 5. Those pieces we have to deal with geometrically in just a second. And then I have a plus c. Now, anytime you see a trig function of an inverse trig function, we can handle this by drawing a little triangle. And it helps to just use some language to describe what we're looking at. This is the sine of the angle whose tangent is x over root 5, and the cosine of the angle whose tangent is x over root 5. So what we need to do is visualize the angle whose tangent is x over root 5 in a right triangle. So here's a picture of the angle whose tangent is x over root 5. That means the opposite over adjacent is x over root 5. So the simplest way to do this is to make the opposite side x and the adjacent side root 5. Now we do need to find the sine and cosine of this angle, and that means we need the hypotenuse. So we take the square of this adjacent side, that's 5, plus the square of the opposite side, that's x squared, and then we square root that result. So our hypotenuse turns out to be the square root of x squared plus 5. And all we're doing there is just making sure these sides satisfy the Pythagorean theorem. All right, so now we're able to find these trig functions of theta. First, we want the sine of the angle whose tangent is x over root 5, and that's opposite over hypotenuse. So this gives me an algebraic expression, x over the square root of x squared plus 5. Now we get the cosine, and that's the adjacent side, root 5, over the hypotenuse. Again, that's square root x squared plus 5. And then we still have our arbitrary constant c hanging around. So I think we're ready to do our final simplifications here. I want to distribute this constant into these parentheses. And one interesting thing to note here is when I distribute to the c, well, that's an arbitrary constant. So if I multiply it by something, that's just some new arbitrary constant, but I'm just going to call that c. So my first term is root 5 over 50 inverse tangent x over root 5. Then in my second term, I have a root 5 in the numerator. So when I multiply that by another root 5, it gives me a 5. That gives me 5 over 50, which reduces to 1 over 10. So the constants are taken care of. All that's left in the numerator is an x, and in the denominator, x squared plus 5. And then I have a plus c, just making a note here that that c is actually a different number than the c from the previous line, but it just doesn't matter because it's an arbitrary constant. And again, I want to point out that because this integral was the integral of 1 over an irreducible quadratic expression squared, this kind of thing can pop out of a partial fractions decomposition problem pretty easily. So we want to be prepared to make that tangent substitution, and in particular, deal with this really tricky issue with the sine of 2 theta that comes out when we first find the antiderivative. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.